Page 2 of HL, complex numbers and polynomials. Number 5, solve for x. So this is one more problem continuing from last page. First thing we want to do is put everything on the left side and leave 0 on the right side. So that'll be x to the fourth plus 2x squared minus 3 equals 0. And normally we can't factor a quadratic without, a cumbersome process such as synthetic division, fundamental theorem of algebra. But here what we can do, there's a little trick, right? This kind of looks like a quadratic, right? If this was, instead of x to the fourth, if this was x squared and this was x, then that would be a quadratic. So what we're going to do is we're going to say, okay, I'm going to change my red x to the 4x squareds. I'm going to change it into an orange x. So this is going to be x squared, and this is going to be x. And now let's solve it, okay? So now it'll be, and now it's a factoring problem. We could put x plus 3 and x minus 1 equals 0. So orange x is either equal to negative 3 or 1. And then if orange x is equal to negative 3 or 1, that means red x squared is equal to those numbers. So if x squared is equal to negative 3, then that means red x is equal to square root of negative 3, which would be I square root of 3. And x squared equal 1. Oops. Then we know x squared equals 1. That leads to x equals plus or minus 1. Okay? All right. Oh, and this one is actually plus or minus square root of I square root of 3. Okay? All right, 5. We'll be able to do the same thing here. So we'll put x to the fourth minus 5x squared minus 36 equals 0. We're going to place that with orange x's. And then we'll factor. So orange x is equal to 9 or negative 4. So red x squared is equal to that. So x squared equals 9 leads to x equals plus or minus 3. X squared equals negative 4 leads to x equals plus or minus I2. Okay. X to the fourth minus 2x squared plus 1 equals 0. We're going to change those into orange x's. So the x squared, the red x squared becomes a orange x. Now we can factor. So that means orange x equals 1. Orange x equals 1. That's equal to x squared. So x is equal to plus or minus 1. Just notice I made a mistake in C. In C, when I factored it, it should be x plus 9. Do you see what I did here? This should be plus 5. This should be plus 5. This should be plus 9. This should be minus 4. And this should be plus 4 and minus 9. So this would be minus 9 plus 4. So this would be plus or minus 2. And then this will be plus or minus 3i. Okay? Sorry about that. 6b, complex numbers. Complex number a plus bi. When b equals 0, the number is real. When a equals 0, the number is purely imaginary. If z equals 2 plus 3i, the real part of z is 2, and the imaginary part of z is 3i. Okay, complex number arithmetic. Okay, so let's go through these. Basically, if you treat I as like a variable, like x, that's pretty much the way you do its math. The book also says that if you treat it like a radical, it's the same thing. So let's see, we're going to add the real parts together, and then we'll add the complex parts together separately. So the real part is a plus c, and the complex part is b plus d. So that's what you get when you add two complex numbers together. If you subtract two complex numbers, you subtract the a minus c, the real part, and then you, for the imaginary part, you subtract b minus d. Okay, and then to kind of FOIL these together, you do the first ones, you do the last one, so bdi squared, and then in the middle you're going to have bci, and you're going to have adi. Let's rewrite bdi squared. I squared is -1, so it's minus bd. Then we can combine like terms in the middle. So, so we'll put AC plus BC plus ADI minus BD. So we could put AC minus BD first. AC minus BD. Okay. All right. Last of all. Okay, so if we multiply a plus bi divided by c plus di by the denominator's conjugate, we could reduce it into a complex number that is only in the numerator, not in the denominator also. So basically what this is doing is complex number division. So let's try that. So the bottom, c plus di times c minus di yields c squared plus d squared, because the i's multiplied together give you -1, the negative and the positive multiplied together give you negative, so it's two negatives, so you get c squared plus d squared in the denominator. On the top, we have a plus bi times c minus di, which is similar to this problem, except for instead of positive d, we have minus d. So we could just recopy what we got above, except every time we see the d, we should, let's see, AC minus BD. Every time we see the D, we need to reverse the sign, because now it's minus D. Plus BC minus AD I. Okay? Let's do number 1 here for 6b1. All we're doing is finding the real parts and the imaginary parts. So the left part that's not multiplied times I is the real part, and the part that's multiplied times I is the imaginary part. So this would be 3, this would be 2i, this would be 5, this would be minus I. 3 by itself would be real, imaginary is 0. 0 itself would be 0 in both. -3 is real, 4i is imaginary. -7 is real, -2i is imaginary, -11i is imaginary, square root of 3i is imaginary. Okay. Number 3, for z equals 1 plus I and w equals -2 plus 3i, find in simplest form. Okay, so z plus 2w. Okay, so all I'm going to do here is I'm going to add this plus 2 of these. So that would be 1 plus I, and then 2w would be -4 plus 6i. And I just like add them up in columns because that's kind of convenient. So I put -3 plus 7i as the answer. Okay. What about z cubed? Z cubed would be 1 plus I cubed. We could use, what do you call it? Binomial theorem expansion here. So we put the coefficients here. The first coefficient, or the first variable is 1, 1 cubed, 1 squared, 1. It's okay. So like in the end, the 1 doesn't do anything, right? What about the I? So this would be I to the 0. This would be I to the 1. This would be I to the 2. And this would be I cubed. Now let's simplify that. Okay. So I to the 0 is 1. So it'll be 1 plus 3I minus 3, because I squared becomes minus 1, so it's minus 3. And then I cubed is the same thing as negative I, so that would be negative I there. And now we're going to combine like terms. So it would be negative 2 plus 2I. Okay? IZW. IZW. So IZW is I times 1 plus I times W, negative 2 plus 3I. Okay, so I, and then the first term would be negative 2. The inside term would be negative 2I. The outside term would be plus 3I. And the last term would be 3I times I, which would be negative 3. Now I'm going to try to simplify the inside. So negative 2 minus 3 is negative 5. Negative 2I plus 3I is plus I. Now I'm going to multiply I times negative 5. I get negative 5I. And I multiply I times I, and that gives me negative 1. So my final answer would be that. Number 4a, simplify I to the n for n equals 0, 1, 2, 3, 5, 6, 7, 9, and also for these negative values. So I to the 0, of course, is 1. I to the 1, of course, is I. I squared, by definition, is negative 1. I cubed would be negative 1 times I, which would be negative I. I to the 4th would be negative I times I, which would be negative 1, which would be positive 1. And then you can see we're going to start the cycle over again. So then it'll be 1, I, negative 1, negative I, back to 1, I. And so, of course, it would continue here. So like negative 1, I to the negative 1 is equal to 1 over I. Okay? 1 over I times I is equal to 1, right? Because 1 over the reciprocal of something times something is always equal to 1. Okay? So since we know that, I to the negative 1, let's see, is also equal to negative I. Because if we multiply I times negative I, that gives us positive 1 also. So that means 1 over I has to be equal to negative I. That's not really intuitive, is it? So, negative I. And then we're back in this pattern again. So like every 4, you're going to have a 1. And then you're going to have I. And then you're going to have negative 1. Blah, blah, blah. Here, this would be negative I. So you see the pattern just repeats over and over again. So it would be 1, 1, 1, 1. Okay? That's it for this page. Page 2.